Welcome back. Today we'll be looking at a CPM Integrated 3 Chapter 8 Lesson 8.2.2 Homework Help. And we'll begin here with our first question, problem 877. But before I begin, all corrections will be made in the comments if need be. And if you do have any questions or concerns about the video, please feel free to leave a comment and I'll do my best to respond as soon as I can. Here we are, 877. Sketch a graph of y equals p of x so that p of x equals 0 has the indicated number of types of solutions. First, we have 5 real. The question is only asking us to sketch the graph, so 5 real solutions means that the function of p of x, when it equals 0, crosses the x-intercept 5 times. That would look something like this. You have your graph, and when p of x equals 0, and you want 5 real solutions, you draw 5 intersections. 1, 2, 3, 4, that would be 5. There you are. That's 1 solution, 2 solutions, 3 solutions, 4 solutions, 5 solutions. Moving on to the next, we have B. They want 3 real solutions and 2 complex solutions. Remember from one of the previous videos that when a parabola or a polynomial function has imaginary solutions, for example, x equals 4 minus I or something like this, it's a function that never crosses the x-intercept. It does not cross this. So when we're given that we have 3 real and 2 imaginary, we need to draw a graph such that there are 3 points where it crosses the x-intercept and 2 points where it doesn't cross the x-intercept, but they do with a vertical shift. So something like that. Why does this work? If we were to move this entire function down just a little bit, we would get something like this. 1, 2, 3, 4, 5. But if you remove the vertical shift, we are left with 3 solutions, 1, 2, 3, and 2 potential solutions that, as of right now, are imaginary, but become real with a vertical shift. Let's move on to C. We have 4 complex solutions. As we've just mentioned, a complex solution is one that never crosses the x-intercept line, so that would look something like this. We have 1 solution, 2 solutions, 3 solutions, 4 solutions, and if we move the graph down towards the intercept here, we would have 1, 2, 3, 4 solutions. But because this is the original graph p of x up here in the white, it has 4 complex solutions. Moving on to part D, we have 4 complex and 2 real. That we have 4 complex and 2 real. And if we were to sketch this, it would look something like that. 2, 3, 4. Oh, that doesn't quite work. We have 1, 2, 3, 4 complex here, and we have 2 real solutions here. Brilliant. Moving on to question E. For part A through D, what is the lowest degree each function can have? So the degree of a function is its highest exponent, and the highest exponent of the function determines how many roots the function has. For example, if we had f of x equals x squared, this would have two solutions, right? So all we need to do to find the degree of any of these functions is to count how many solutions are there. So for part A, this has 1, 2, 3, 4, 5 roots, so it has a degree of 5, and you cannot go less than that because once it has a degree of 4, there's only going to be 4 solutions here. For B, we have 3 real and 2 imaginary, so this must also have a degree of 5. For C, we have 4 complex solutions. There are 4 solutions to this, so it has a degree of 4, and it can't go any less than that. And finally, we have 4 complex and 2 real. That makes 6 solutions, so it has a degree of 6. Moving on here to the next question, we have question 8-78. For each of the following sets of numbers, what is the equation of a function that has these numbers as roots? A, here we have -3 plus I and -3 minus I. Here we had, for A, -3 plus I and -3 minus I. So here we can actually, because these are the roots, these are the solutions that our problem has, we can rewrite this like this, with x equals whoops, 3 minus I, and you would be tempted to write something like this, where you move this x to both sides for each of these, set them equal to 0, and then set this whole thing equal to 0, and multiply this out. But if we remember from the previous video with the 2 methods, we can use, I believe it was, Hugo's method. And how that works is we can move this 3 here on the other side to isolate this imaginary term. We can square both sides like this. And if you're wondering how I did this, that is x plus 3 squared, which is equal to x plus 3 times x plus 3. And we have x times x. I'm going to use the FOIL method here. We have x times x, x squared, plus 3x, plus 3x. For this, x times 3 and x times 3, and then we have plus 9. Or, if you didn't want to use the FOIL method, because we have this form of a plus b squared, we could have used a squared plus 2ab plus b squared, and we would have gotten the same solutions. Now that we have this, we can rewrite our I squared term as -1, because I equals negative square root of run, and squaring both sides gives us -1 for I. So we have x squared plus 6x plus 9 equals -1. Add 1 on both sides. X squared plus 6x plus 10. And we'll set this equal to y to show that it is a graph. It is a function that is graphed. We'll continue here with part B of this question. We have the roots 5 plus square root 3 and 5 minus square root 3. Here we are. We can set these both equal to x to make it a little bit easier to visualize. Square root 3, x equals 5 minus root 3. And we can use the exact same method as before with the imaginary number, but this time we isolate the square root, because when we move this 5 over and we isolate the square root and then we square both sides like before, here On the right side, we get root 3 squared. These two cancel each other out, which gives us just plain 3. And using the exact same method as before, I'll multiply this out. That would be x squared minus 10x plus 25. And subtracting 3 on both sides of the equation will give us, and I'll write this with y to show that it is a function, or equation, equals x squared minus 10x plus 22. And here, we are given the option to view the solution, and we can see that it is correct. All right. For part C, here we have a lot of roots, -2, square root 7, and square root of -7. Coming back here, we have part C. We have, what were they? -2, negative root 7, and positive root 7. Alrighty. Here, we can set all of these equal to x. That would be like this, and like this. Oop. And from here, we can multiply them all together and set them equal to 0. So that would be, first let me rewrite this. That'd be 0 equals -2 minus x. That would be 0 equals negative square root 7 minus x. And 0 equals square root of 7 minus x. Now we can write all this and multiply them out. We have -2 minus x. We have -7 minus x. Minus x. And we have root 7 minus x. The first thing I'm going to do is actually take out a -1 from this factor. Rewriting it, that would give us negative square root 7 plus x. And writing it again down here, we can move this negative all the way up to the front. We can actually multiply it into this one. So I'll write all those steps out. So it'd be -2 minus x, square root 7 plus x, square root 7 minus x. And you may already be able to see why I've done that. We have 2 plus x, 7 plus x, and square root 7. Forgot the parenthesis, square root 7 minus x. And you can see that the reason I've decided to do this is now we have a very clean difference of squares. We can apply this again, which will give us y equals 2 plus x. This squared, our a is square root 7. That squared is just 7. And x squared is x squared. That gives us minus x squared. And this, finally, we can use the FOIL method. That will give us, let's see here, 14 minus 2x squared plus 7x minus x cubed. And now I'll rewrite this into standard form, which will give us negative x cubed minus 2x squared minus 7x plus 14. Ah, this is supposed to be a plus here. Yeah, there it is. Because this 7 times x, and that should be it. Moving on to the next. Finally, we have part D. We have solutions of 4, -3 plus I, and -3 minus I. Writing that down, That graph you saw was me double checking my work. We have D. That'd be 4, -3 minus I, and -3 plus I. Just double check. -3 minus I plus I. Fantastic. All right. I'll rewrite this with this notation, just so it's a little bit easier to see. And now that I've written this all down, we can begin solving. So I'm going to, this time, actually move everything from the right side to the left. So I'll rewrite this as x minus 4 equals 0, x plus 3 plus I equals 0, and x plus 3 minus I equals 0. Now, you could do this. You could write this out as y equals, or 0 equals x minus 4, this entire long thing, and multiply it out completely. But this just looks like a pain to me. So instead, I'll use Hugo's method that I used prior. I'll use this one. I'll move this over. So that'd give us x plus 3 equals I. I'll square both sides. Like that. And this is correct, but only if we're working with these two. Because we have this additional x minus 4 term, what we actually have to do is multiply what we have just gotten by x minus 4. Now, if we do multiply this together, we will get, here we are, x cubed plus 6x squared plus 10x minus 4x squared minus 24x minus 40. And here we have x cubed. 6 minus 4 is 2. And 10 minus 24 is negative 14. Minus 40 equals, and I'll set this equal to y to show that it is a graph. Here we are. Moving on to question 8-79, we have consider the function y equals x cubed minus 9x. What are the zeros of the function? And we're given a hint here to factor. And next we're asked to sketch this graph. So first and foremost, let's write this equation out and begin factoring like suggested. All right, here we are. Now, if we factor this out, we will get, to pull one x out, that'd be an x. And we can confirm this is correct by multiplying this x back into the parentheses. That'll give us x cubed minus 9x, which is exactly what we had before. Now, we can notice that this has the form of the difference of squares. How do I know? X squared is a perfect square, and 9 is also a perfect square. 3 times 3 is 9, x times x is x squared. And they're separated by a minus sign. So that gives us a equals x, b equals, here we are, 3. So that when we do x plus 3x minus 3, we will get x squared minus 9. Because when we multiply this out, we get x squared minus 3x plus 3x minus 9. These two cancel, and we're given the final. So moving back here, we have y equals x plus 3, x minus 3, and we can find our roots. Using the zero product property, we can set each of these to 0 and solve for x. So we have x equals 0, that's this first term. X plus 3 equals 0, that gives us x equals negative 3, that's this second term here. And finally, we have x minus 3 equals 0, which gives us x equals 3. That's our third term here. We have x equals 0 and 0 equals, x equals 0 and plus or minus 3. All right, let's check our answer. And there we are. Plus 3, minus 3, and we have our 0. Now we're asked to sketch the function. For this, I'm going to really quickly create a table. I'll show how to do that with one value and complete the rest of the table on my own, so you don't have to sit through that. I'll go from -4 to +4. Why not? So we have, let's start with -4. Plugging this into the equation. Plugging it into here would actually be a lot easier because there's less terms to work with. So that would be -4 cubed minus 9 times -4. That gives us 64, -64 plus 36. And that should give us that's 14 minus 6, that's 8. -28. Let me double check that real fast. Yes, so we have -28. That's going to be far too big to graph, but it's good to know. I'll continue with the rest of these values, and I'll cut back when I'm all done. Okay, I have created their table, and now to create that graph. These values are really large, so I'm going to make the y intervals a lot larger. So I'll do here 1, 2, 3, -1, -2, -3. And for the y-axis, I'll use intervals of 5. We have here 5, 10, 15, 20, 25, and I'll need to move this y, 30. Here we are, -5, -10, -15, -20, -25. All right. So we have -4, comma, -28. So that's right about there. 3, 0, that's our roots. -2, +10, that's right there. -1, 8, that's right there. 0, 0, 1, -8, that's right about there. And notice how it inverts about x equals 0. Right about there. We go back to 0 and up to positive 28. Ooh, that looks really bad. Alrighty. And if we were to sketch this, it would go something like that. And it would shoot off forever. Kind of missed, didn't I? Yeah, it's fine. Alright, question 8-80 now. Solve each of the following equations for x. Here we have 171 equals 3 times quantity 5 to the x power. So let's write this down. 171 equals 3 times 5 to the x power. Let's begin by isolating the exponential term. We have 171 over 3 equals 5 to the x. Now we can take the logarithm of both sides. So we have log 171 over 3. And we have here log of 5 to the x. And we know a property of logs is when you have a logarithm of a to the b. This is equivalent to b times the logarithm of a. So we can rewrite this logarithm on the right as 171 over 3 equals x log of 5. Now, finally, to solve for x, we divide log 5 on both sides, and we're given a final answer of the logarithm of 171 over 3 over the log of 5. Nice and easy. We can rewrite this. It's not really necessary, but we can rewrite this as the log of 171 minus the log of 3 over the log of 5, because the log of a divided by b is equivalent to the log of a minus the log of b. This just makes it look a little more professional. We could actually simplify this even more. Actually, nah, that's as simple as it gets. Here is our final answer. The next part of the question, it's a different part entirely. Solve each of the equations for x. Here we have b is 171y equals 3x to the 5th. So the first thing I'll do is isolate this x term, because that x to the 5 looks real ugly. So for part b, we have 171y equals 3x to the 5th power. I'll divide by 3. That gives us 171 over 3 equals x, not the y, equals x to the 5th power. And now we can take the 5th root of both sides. Here we have the 5th root of 171y over 3. There is our answer. So with problems with exponents, sorry, problems with exponents like this, or like this, the first thing you gotta do is isolate the term with the x in it, or with the exponents of x. Very crucial. Quick little note, I noticed this after solving. 171 divided by 3 is actually 57. So for part A, you could rewrite this answer as x equals the log of 57 over the log of 5. And for part B, you could rewrite the answer as x equals the base, the fifth root of 57y. This was also a possibility. All right, here we are on 881. If f of x is equal to x squared plus 7x minus 9, calculate the values in parts A through C below. So let's write this function first. We have f of x equals x squared plus 7x minus 9. And part A asks for us to find f of negative 3. Yes. When you plug negative 3 into x like this, what you're actually doing, make sure you write this more formally, find f of negative 3. When you write this, you have negative 3, and you're substituting negative 3 for everywhere that an x exists. So here, negative 3, and always use parentheses, always, 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 minus 9, and this becomes 9 minus 21 minus 9, and this 9 and this 9 cancel out, so that makes f of negative 3 negative 21. Part B asks for f of I. Has to find f of I. So when you plug I into this function, of course, you need to replace every single instance of x with this I. So we have I squared plus 7I minus 9. Or just to stay on principle. As we know, I squared is negative 1. This becomes 7I minus 9. And this simplifies to f of I equals 7I minus 10. Moving on to part C, we have f of negative 3 plus I. And I like rewriting this with the positive term in front. It's standard to write complex numbers as real plus imaginary. But just for the sake of this, it's just a preference. I like to write it as like this. But it doesn't make a difference. The math will turn out the same. Here we have I minus 3 squared plus was 7 I minus 3 minus 9. First, let's work with this one. I'll actually work on them individually and then add them back together. So working on this one, we have, I'll actually write it here on the side, I minus 3 squared. I'll use the property that we have already discussed. A plus B squared equals A squared plus 2AB plus CB squared. And with this, we can say that this is I squared minus 6I plus 9. The next part is 7I minus 3 times quantity I minus 3. That gives us 7I minus 21. And finally, we have the negative 9. So if you plug all that in, we get I squared. Oh, I can simplify this I squared now, can't I? This becomes negative 1 minus 6I plus 9, which becomes 8. minus 6i. If that was a little bit confusing because of the backtrack, I just noticed that I could have simplified this into -1. I plugged it in here, subtracted -1, or summed -1 and +9, which gives 8, and that -6i stays the same. So here we have 8 minus 6i plus 7i minus 2i. It's always good to use parentheses when distributing something like this, because you could make a terrible mistake if this plus was actually a minus sign. So always when you do this, use parentheses and minus 9. Here we can add like terms. Oh, why did I put I there? Should be 21. Okay, now we can start adding like terms. First, let's rewrite this to remove the parentheses. Then let's rewrite this so that all the like terms are together. That'd be 6i plus 7i plus 8 minus 21 minus 9. Now we can see clearly that negative 6i plus 7i is positive I, and 8 minus 9 is -1, minus 22 is minus 21 is -22, -1 minus 21 is -22. And if you want to rewrite this in the standard form, or how you're supposed to write this, it would be -3 plus I, f of -3 plus I equals -22 plus I. So this would be your answer here. All right. All right. 882 looks like a doozy. After finding out that her kitchen does not conform to the industry standards, Lashaya is back to the drawing board. Where can she locate her sink along the counter in the top of the diagram at the right so that its distance from the stove and refrigerator is as small as possible? Will this location make her perimeter less than 26 feet? Show all work. All right. Now, to solve this, I'm going to draw a figure and kind of demonstrate what I'm trying to do here. So, here is this figure that I've drawn here. It has all the same sides. This here is the stove, this here is the refrigerator, and this here is the sink. So we're trying to see, where does this point need to be for there to be the shortest path from point F to the sink and from the sink to the stove. So what you could do to actually visualize this is flip this line here upside down. So what you actually end up doing is forming this. This is right, and now this here is right. This is the new stove. You can invert this one like this. Here, we see that these two angles are vertical angles. We have two angles here, angle, angle. We can see that this triangle here is similar to this triangle here. Right? These two triangles are similar. So to solve this, we basically need to find the point on this line up here that makes this triangle and this triangle similar. So we're given this triangle and this triangle, and the shortest path is when these two triangles are similar. Because when they are similar, you can flip this triangle over this top line, and you'll get a straight path, which is the shortest distance between the two. So we are given that this side length here is 6, this side length here is 3. This side plus this plus this is 11. So we'll call, if we go from left to right, we can call this one 11 minus x, and we can call this one just x. So we're trying to see a value of x that satisfies x over 6 equals 11 minus x over 3. To solve this, let's multiply by 6 on both sides. That gives us x equals 22 minus 2x. And if you're wondering how I got that answer, I did 6 times 11 minus x over 3. This 6 over 3 becomes 2 over 1. And because this denominator of 1 will go away, we have 2 times 11 minus x, which gives us 22 minus 2x. Now here, we can add 2x on both sides, which gives us 3x equals 22. And dividing both sides gives us 22 over 3, which is equivalent to, let me get a calculator here. Or we might not need a calculator. 7 times 3 equals 21. That gives us 3 and 1/3. Sorry, no. 7, because it's 7, and 1/3. That gives us 7.33 repeating for x. And there we are. So if this point here, or this whole line is 11, then this x value right here is 7.33 repeating, or 7 and 1/3. Alrighty, now that we know that our x equals 7.33, we are tasked to find this side. To do that, we need to first find these two angles. So then we can find this angle, and we need to find this side, and then we'll have everything we need for the law of cosines. So first, let me find these side lengths. So we have here, for this side, I'll solve this entire triangle first, actually. We have 6 squared plus 7.33 squared equals c squared. And when we solve for the c, we take the square root of the whole thing. And plugging this into a calculator gives us a c side of 9.47 feet. Now we have our second side, which is this one. Actually, no, I'll solve this angle first. This angle, we can use a tangent where this is the opposite and this is the adjacent. And I'll call this angle alpha. So we have the tangent of angle alpha equals opposite 6 over adjacent 7.33. Then to solve for alpha, the angle, we take the tangent inverse of both sides. That would be alpha equals the arctangent or tangent inverse of 6 over 7.33, which gives us an angle of approximately 39.3 degrees. Now for this angle, I will call beta. This is the opposite, this is the adjacent, so we have the tangent of beta equals opposite 3 over adjacent 3.66. And we take the arctangent, or the tangent inverse of both sides. That gives us beta equals arctangent 3 over 3.66. And this gives us an angle of approximately 39.34 degrees. Now that we have these two angles, we can solve for this third angle. I will call a gamma. So we have gamma equals, and how we'll solve this is this entire line is 180 degrees. So we can find what this angle in the middle is by doing 180, which is the entire thing, minus alpha minus beta. So this becomes gamma equals 180 minus 39.3 plus, sorry, this is plus 39.34. Putting that into a calculator gives us approximately, oh, did I do that right? No, I didn't. Approximately 101.36 degrees. Ooh, I've gotten a little bit ahead of myself, haven't I? I haven't found this side yet. I'll do that now. So we have the square root of 3 squared plus 3.66 squared equals c. And I took the square root right away. And putting all that in, 3 squared plus 3.66 squared. Oh, why did I put that at fifth? There you go. That gives us a side length of 4.73 feet. Just to recap, this side A equals 9.47. This side B equals 4. What did I say? 73. We have this angle alpha, that is 39.3 degrees, and this angle beta, that is 39.34 degrees, and this angle in the middle as being 101.34 degrees, or 36 degrees. Apologies. Now that we have this, we have everything we need for the law of cosines. I'll name this side here C. So we have big C equals a squared plus b squared minus 2ab cosine gamma. That makes our equation, oh, sorry, this is c squared, apologies. And then we can square root both sides. That gives us a squared plus b squared minus 2ab cosine of gamma. Now we can solve this. We don't know our c still. We do know our a. It was 9.47, if I'm not mistaken. Yes, it is. Our second side plus was 4.73 squared minus 2 times 9.47 times 4.73 times the cosine of gamma, which is 101.36 degrees. And we get an answer of, let me put this into the calculator. We get C equals 11.39 feet. Now we add all them up. That's 9.47 plus 4.73 plus 11.39. And putting all of that together, 73 plus 11.39 gives us 25.59 feet. So the side lengths of her kitchen triangle is below 26 feet and means she is within regulation. Last but certainly not least, we have our final question. 8-83. Guests are arriving for a show when the theater manager realizes he forgot to turn on the air conditioning. The guests are very hot. At 2:04 p.m., the manager turns on the air conditioning. It is 85 degrees Fahrenheit in the theater. Part A. At 2:15 p.m., the manager announces that he has bad news. Using average rate of change, he predicts that the theater will not cool to a comfortable 70 degrees Fahrenheit until 3 p.m. What calculations did the theater manager make? What was the temperature at 2:15? So we're given that at 2:04 it is 85 degrees Fahrenheit. And according to the calculations of the theater manager, we will not reach 70 degrees at what was the time again? 3 p.m. All right. So we know, I'll simply state it again, that at 2:04 it's 85 degrees, and the manager says that it won't become 70 degrees until 3 p.m. So we need to calculate the number of minutes that have passed from 2:04 to 3, the change in the degree, Fahrenheit change, temperature change, and we can use the rate of change formula, delta y over delta x, to calculate the slope of a line, and then we can find what it is at 2:15. So the difference from 2:04 to 3 is 56 minutes. And the difference between 85 degrees Fahrenheit and 70 degrees Fahrenheit is 15 degrees Fahrenheit. But it is very important to note that this, when we plug it into the function, will become negative 15. And I'll quickly explain why. The equation, this part delta y is found by doing y1 minus y2, and that goes over x1 minus x2. In this case, we can consider 2:04 to be our start time. So we have x equals 0. And we can say that our time, 3 p.m., is x equals 56. Then, at 3 p.m., it'll be 70 degrees. I'll start with this one. 2:04 is 85 degrees. So 85 degrees will be our y equals 85. And our 70 degrees will be y equals 70. So to solve this, we have y1, 85, minus y2, 70, over x1, which is 0, minus our x2, 56. That gives us 15 over negative 56. And pulling out the calculator shows us that this is roughly negative 0.267. We have just calculated degrees per minute. So now we can use this knowledge to find what the temperature must be at 215. The difference here between 204 and 215 is, let's see here, 11 minutes. And since we know that the change in temperature is negative 0.267 degrees per minute, we can say 85 minus 0.267 times 11 minutes. Plugging that into our calculator gives us 82.063. Now, we could do this and find an exact answer using the fraction up here. That would just be, we would just replace this value with negative 15 over 56. Which would give us a much closer answer of 82.05357, etc. Second part. As the air conditioner continued cooling, the manager recorded these actual temperatures. Here the question is asking, what was the average rate of change after 3 p.m. until the temperature reached 70 degrees Fahrenheit? Why was the manager so far off on his predictions? The reason he was so far off is that he incorrectly assumed that the change in temperature was linear. He assumed that if the temperature is decreasing, it is decreasing at a constant rate. That means he is using the value that we have found and assumed that this must be how much the temperature will drop per minute no matter what happens. But as we can see from the table, the temperature drops 2 degrees in like 39 minutes, which is definitely not the negative 0.27 degrees that we found before. Now, the question is asking for what the average rate of change was after 3 p.m. We can calculate this by doing the exact same as before, where we plug in one time, the other time, and one temperature and the other temperature, just like we did before. So here we want the same thing. We want degrees over minutes. The change in minutes was 39 because the difference between 3:01 and 3:40 is 39 minutes. And at 3:01 it was 72, and at 3:02 it was 70. So our change is a drop by 2, so that means we have negative 2 over 39 minutes. That gives us a final approximate answer of, let's see here, negative 0.051 degrees per minute. All right. Is there any more? Yep, that concludes the video. If you have any questions, please leave them in the comments. And if I find any errors in my work, I will post corrections in the description. Thank you very much. Have a nice day. All right, now for part B, we have, as the air conditioner continued cooling, the manager recorded these actual temperatures. Here we're given a table, and then we're asked what was the average rate of change after 3 p.m. until the temperature reached 70. Why was the manager so far off in his prediction? So, this second part of the question is really quick to answer. He was wrong because he assumed that the temperature change was linear. When we look back here, we see that we found that the manager thought that the temperature change was 0.267 degrees dropped every single minute. And he assumed that was the case, but he was wrong. The change in temperature is exponential. We can see this because from 301 to 340, that's 39 minutes, the temperature only drops by 2 degrees. Or more accurately, from 301 to 327, that's 26 minutes, it only dropped by 2 degrees. That is a very small change. Now, when it asks us to find the average rate of change from 3 p.m. to when it reached 70 degrees, it's asking us to find it from after 3 p.m., which is 301, to when the temperature reached 70 degrees, which is here. This is the first instance of 70 degrees, here at 327. So going back, we want the exact same results. We have m equals degrees over minutes. We know the degrees drop by 2, and 26 minutes pass. Calculating this gives us negative 1 over 13. And plugging that into a calculator gives us approximately negative 0.077 degrees per minute. That is definitely a lot less than the negative 0.267 that we found earlier.